Hello everyone, and today we're going to be doing the 2016 December contest silver problem, counting hay bales. For those of you who haven't read the problem yet, the problem basically states that Farmer John has arranged his N hay bales at various points along the one-dimensional road running across his farm. And the problem is also going to give us Q queries, and each query is going to give us a start position and an end position. And our job is to find the number of hay bales between that start position and that end position. So to get a better sense of the problem, let's draw the sample case out. Okay, so first I'm going to draw a line representing the one-dimensional road that Farmer John has. And we're going to draw a bunch of tick marks representing the positions of the line. And in this case, we have a hay bale on position 3, we have a hay bale on position 2, we have a hay bale on position 7, and we also have a hay bale on position 5. Okay, so we have these hay bales. Now we're going to answer the queries. So the first query is going to be 2, 3. So it's saying from position 2 to 3. So if we look at this interval, we have 2 to 3 right here. And there are 2 hay bales in that position, in that interval. So our answer would be 2. And we can see that indeed our first answer is 2. Okay, so the second query is going to be 2, 4. So if we look at the interval 2 to 4, we can see that we still have 2 hay bales between that interval. So our answer would be also 2. And as we can see, it's 2. And the third is going to be 2, 5. 2, 5 is going to have 3 hay bales. So our answer would be 3. Let's see, 3. So how do we go about solving this problem? Well, the first thing that came to my mind is that we can just cycle through all of the positions in the interval, and if there's a hay bale, we can add it to the count. So let's say our interval was 3 to 6. We're going to cycle through each of the positions. We're going to say I from 3 to 6. And each time we get a hay bale, we're going to increment our count. So we're just going to cycle using a for loop for each of the queries. But that would not work because we would have 100,000 queries and we have 10 to the 9 positions. And this would be 10 to the 9 times 100,000, which would be a giant number, and it would obviously time out for most of the cases. And so this solution would solve the first case, but the other case, not so much. So this is definitely not a valid solution for this problem. Now the second thing that came to my mind was prefix sum. So, for those of you who don't know what prefix sum is, I've provided a link in the description, and if you go to that link, you can learn about prefix sum. But right now, I'm just going to go over it briefly. So for prefix sum, we're going to have an array representing all the positions on this position line. So just going to have an array. It's going to be first, second, third, 6, 7, 8. So what prefix sum can do, so what prefix sum is I'm going to record how many hay bales are from the current position to the first position. It's always going to be to the start. So for number 1, we have 1 to 1. The interval 1 to 1 has 0 hay bales. For the second index, we have 2 to 1. How many Haybales are in here? We have 1 Haybale, because 1 is on 2. And then we have 3 to 1, which we have 2 Haybales. And then for 4, we also have 2 Haybales. 5 is going to be 3 Haybales. 6 is going to be 3 Haybales. 7, 4, 8, 4, 9 is going to be 4. So how is this array any useful to the problem that given two intervals that might not start from the start? How is this useful? Well, what prefix sum can do is that we can first take the number of Haybales from the end position to the very beginning. So in this case, we have 6, and we're going to take the number 3, and then we're going to subtract it by the start minus 1 interval to the start position. So that was, the start is 4, minus 1 is 3. So we're going to subtract it by this number. And if we subtract that, we have 3 minus 2, which will give us 1 Haybale from the position 4 to 6. And if you think about it, it does make sense, because the first interval we take is this big one subtracted by this one, so we're only left with this one. And this seems like a valid solution. However, we can see that the positions go up to 10 to the power of 9. And to make an array that big, it's just not allowed. And then we're not allowed to cycle through 10 to the 9th power. And that solution is probably going to only pass half of the case, and then time out for the rest of the case. So this will pass about half the case, because the positions can go on for way too long. So this is not an entirely valid solution, but it is definitely better than the first solution, which is to cycle through everything. The actual solution is going to be using binary search. So for those of you who don't know what binary search is, I've also provided a link in the description for that. But what binary search is it's an algorithm that searches through a sorted array. And then the actual algorithm we don't really have to implement, because in C++ we have 2 functions. We have lower bound and we have upper bound. And these two functions is gonna help us use binary search without actually implementing it. Okay, so let's say our query was 4 to 8. So let's say how many Haybales are between 4 to 8. Now, let's first put this into an array. Put the Haybales into an array form. So 2, 3, 5, 7. This is gonna be easier to see. And if our question was 4 to 8, all we need to do is we're gonna find where 4 is in that array. So for 4 is gonna be between 3 and 5. So let's just say 5. And then 8 is gonna be the biggest. It's gonna be here actually, an imaginary value in this array, because 7 is too small for it. So if we count the indexes for these 2 points, we have 1, 2, 3 for the first one, and 4, 5 for the second index. And if we do 5 minus 3, we're gonna get 2 as our answer. 2 Haybales. And you can see a pattern here. We're always finding the element that is larger than the index we're given. So let me do another example. Okay, so let's say our indexes were 3 to 5. So we can find 3 in the array. We can see it's over here. So should we include this one, or should we include the next one? So that is the difference between lower bound and upper bound. Lower bound is going to give you the element that is equal to or greater than the given element. It's going to give you the first element that is equal to or greater than the given element. Now upper bound is only going to give you the element that is greater than the given element. So in this case, for 3, should we use upper bound or lower bound? Well, since we're starting with 3, why not include it? Because 3 is one of our Haybales. So let's use lower bound for this one. So 3 is going to point to this element. And if we find 5 in the array, should we use lower bound or upper bound? Well, 5 is one of our elements, and we can see this is the interval. However, this wouldn't work because if we subtract 3 and 2, we're going to get 1. So 3 is the index of 5 and 2 is the index of 3. So if we subtract 3 minus 2, we're going to get 1. And we can see that it's inclusive for this one. And if we subtract it like this, we're not going to get an inclusive answer. So for 5, we can make it upper bound. So it's going to point to 7, even though 5 is the same. So upper bound only give us the number that's greater than the given element. So now it should work. Now 7 has an index of 4. 4 minus 2 would give us 2, which is how many Haybales are in this interval. So the binary search algorithm actually has a complexity of log n. For each search, it's going to give us log n complexity. And multiplying that by the q queries, and each query is going to be 10 to the 5th. So this would be log n times q, which is log 10 to the 5th times 10 to the 5th, which is going to be small enough to help us pass every case in this problem. Now let's look at the actual code and implementation of this problem. So first of all, I'm going to read in the n and the q. Then I'm going to make a vector Haybales. I'm going to read in every element in that Haybales using cn. Then I'm going to sort the Haybales from lowest to greatest so we can actually binary search it. Then I'm going to cycle through every query. In each query there are two numbers. There's A and B, and A will represent the start and B will represent the end. Then I'm going to perform the actual lower bound, upper bound. And for A index, it's going to be the index that we find the element A in the array Haybales. So we're going to do lower bound, Haybales.begin.end. I'm going to pass in A. This will give us an iterator. So to convert that into an index, we need to subtract it by the Haybales.begin. And we're going to do the same for B, except we're going to use upper bound this time. And then that's it. And then we're just going to see out the end index minus the start index giving us how many Haybales are between those positions. Okay, to sum it up, for this problem, I have included 3 different solutions, and only the binary search solution works. This problem shows that a problem can have many solutions to it, and the hard part is going to be finding the most quickest solution and the most elegant solution. Hope you guys enjoyed the video, and I'll see you in the next USACO problem.